Hi, and thanks for joining me in this video on error analysis. We're going to talk about statistics in this video. We're going to look at a case where we measured CDs and we have an estimate of their size. The best estimate after we made several measurements is 12.8 millimeters. That's our average. And we measure another CD and we come up with an average, or not an average, but an actual measurement of 116 millimeters, and that's our best estimate of the size. So given that, we have an average of 112.8, and we measured another one that's 116 millimeters. Is that measurement acceptable? Well, it comes down to how much precision we want and how much random error we're willing to accept. If you recall from previous video, when we did this calculation of several CDs and came up with the average 112.8 millimeters, we also came up with a standard deviation of 2.9 millimeters. So that is we can think of that as kind of our average deviation. And that gives us an error range for one standard deviation of anywhere from down to 109.9 millimeters and all the way up to 115.8 millimeters. So if we say we're using one standard deviation as our acceptable standard, then 116 falls just outside of the 115.8, the higher end of our measurements. And remember, we said that for one standard deviation, our level of uncertainty is 68%. In other words, we said that 68% of all measurements will fall within that, and there will be 32% that fall outside of that for one standard deviation. If we pick two standard deviations, then we're willing to accept more randomness and less precision. And that would give us, let's see, 2 times 2.9 is 5.8. So that means that we're willing to accept values that are 107 millimeters all the way up to 118.6 millimeters in diameter for those CDs. So that means that 95% of all our measurements should fall within that, and only 4.6% should fall outside. So we're willing to accept more measurements, but we're also willing to accept more randomness and less precision. To calculate the discrepancy between these two, of course, we look at our measurement, which is 116 millimeters. We look at our average, our best estimate, which is 112.8, and take the positive difference between those. So 112.8 minus 116 gives you 3.2, and that's our discrepancy. So the discrepancy is significant, or it's not acceptable, if it falls outside our level of uncertainty. So if we say our level of uncertainty is one standard deviation, we calculated that to be 2.9 millimeters. So yes, a measurement of 116 falls outside of that range. The probability that a measurement will fall outside the acceptable level of error is simply 1 minus the probability that it will fall within, depending upon the number of standard deviations. So for example, for one standard deviation, the probability that our measurements will fall outside of our accepted standards is 1 minus 0.68. That's the probability for one standard deviation. That means about 32% of our measurements will fall outside, and 68% we're willing to accept. If we increase the number of standard deviations that we're willing to accept, then that increases the chances that the measurement will fall within the level of uncertainty, and it decreases the chances that our measurement will fall outside the level of uncertainty. So in other words, it increases the randomness of your errors, and by definition, you have a lower precision. And this graphically shows that. Here's a small t, here's a big T. In other words, we're only accepting on the left only one standard deviation, so it is very close to the true value, and most measurements, 68%, fall within one standard deviation. So you've got good precision and small random errors. But if you increase the number of t's, in this case we're looking at 3 standard deviations, then you get more of your values measurements falling within your acceptable standards, but you got poor precision, which means you got a lot of random errors. To calculate if a discrepancy is significant, you have to figure out how much uncertainty you're willing to accept. Is it 1 standard deviation, 2, 3, or whatever? To calculate the discrepancy, of course, you take the best estimate or the average and subtract from that your experimental or your measurement. So that would be simply 112.8 minus 116, which gives you 3.2 millimeters in this case. To calculate our t-value, we take the discrepancy, the best estimate or the average, minus the measurement or the experimental, divided by your calculated standard deviation for the set, and that'll give you a value of t. In our case with the CDs, as I said, our discrepancy is 112.8 minus 116. We had a standard deviation of 2.9. That gives us a t-value of 1.1. In other words, this measurement that we just made falls 1.1 standard deviations on our curve. So are we willing to accept that or not? It depends upon where we draw the line. If we want 1 standard deviation, 68%, and that falls outside. That's 1.1 standard deviations. So when we do a test of significance, we have to figure out what kind of confidence level we want. In other words, we want to figure out how many standard deviations we're willing to accept. Then we have to calculate the t-value and compare those, the number of standard deviations versus the t-value that we get. And if the t-value is bigger than the standard deviations that we're willing to accept, then the discrepancy is significant and we have to throw out that measurement. Here's an example with our CDs. We came up with an average of 112.8. That was the best estimate. 116 is our experimental or our measurement. And as a result, let's see, we did a calculation of this population. We found the standard deviation was 2.9 millimeters. So 2.9 millimeters either side. And you can see that when we calculated for 116, we got a t-value of 1.1 standard deviations. And that's greater than 1. So that falls outside of what we're willing to accept. So that's a little bit how we use standard deviation and how we use means and discrepancies to figure out the spread or the randomness of our measurements and if we're willing to accept the measurements or not.